Okay, now on to question 7. Stating an assumption, show that the age of the universe can be given by 1 over the Hubble constant. Okay, so remember that Hubble's law says that velocity is equal to the Hubble constant times distance. So if we assume that velocity is constant, then time must be distance divided by velocity. So that's our assumption. We're assuming constant velocity of stuff, or assuming constant rate of expansion. That implies that time is equal to distance divided by velocity, and velocity is equal to h0 over d. Therefore, time is equal to d divided by h0 d, which equals 1 over h0. Part 2, quasars are extremely bright objects in the night sky. Here is a quasar discovered in 1960, which is really quite far from Earth and has this high redshift. Use this information to estimate the age of the universe, so specifically use this information in bold. And we're told what a light year is, because note these units, this is in light years. So how do we go about this? Note this is a part 2, a kind of part II. So it very much follows on from the last thing. So we know that t is equal to 1 over h0. And we know that since v is equal to h0 d, then then h0 is equal to v over d, and 1 over h0 is equal to d over v. So therefore, the time that we're looking for is equal to d over v, which in this case, we need to know that, because we're not told the speed directly, we're told the redshift. So we'll use the redshift equation. V over c is equal to delta lambda over lambda, which in this case equals 0.36. So therefore v is equal to 0.36 times c. So I can substitute that in. T is equal to this distance, 4.6 times 10 to the 9. That's in light years, so we'll multiply that up by 9.46 times 10 to the 15. That's the information we're given. And then we're dividing that by 0.36 times the speed of light from the formula sheet, 3 times 10 to the 8. And I'll check that in the calculator. And I've got 4.03 times 10 to the 17. And this will be in seconds, because the units I've used are meters and meters per second for the speed of light. Yeah. So that's in seconds. If you were curious and you want to check your answer, you could just convert that into years so that you can just double check. So I'm going to chuck that into the calculator and just see. And it's given me an answer of about 13 billion years. So that feels to be in the right sort of ballpark. I think that's relatively straightforward for 4 marks. I suppose several steps in the calculation, so a few places where the algebra could go wrong, but it's straightforward algebra. These are expressions with only a couple of variables. Okay, part B. Astronomers studying a spiral galaxy estimate from their observations that its mass is this. calculate the theoretical orbital speed of dust particles orbiting at this distance from the center of the galaxy. Theoretical orbital speed. So what we do to calculate that, if we think about Newton's second law, F equals ma, and the equation for centripetal acceleration, which the version we want in this occasion is v squared over r. If we combine those, that tells us that centripetal force must be equal to mv squared over r. And we also know from Newton's gravitational law that that sim force must be provided by gravity, and therefore we can write that sim force as gmm over r squared. So we're simply going to equate the two. We cancel those small m's. We can cancel the r with the squared, and that gives us then an expression for v. V is going to be equal to the square root of gm over r, which is equal to, I'm going to go ahead and write the substitution, 6.67 times 10 to the minus 11, multiplied by the mass we're given, 4 times 10 to the 40, divided by that given radius, 1.2 times 10 to the 21. And once again, chuck that all in the calculator and see what we get. It's hard to have an idea of what a sensible answer would be for this question. So the answer I've got is 47,000 meters per second. And as I said, very difficult to know whether that's correct. You know, we're expecting a big number, but you know, once you're dealing with things moving through space, 47,000 meters per second isn't a radically huge number. So we'll just have to rely on the calculator skills and hope that we've got that one right. Part 2, the measured velocity of the dust particles is found to be greater than this theoretical value. Explain how astronomers account for this discrepancy. So this is the standard sort of evidence that we have for the existence of dark matter when we analyze the motion of dust or anything really that is far out from the center of galaxies orbiting the center. We find that it's typically moving much too quickly to be held by the galaxy's gravity, and the proposed explanation for that is the existence of matter within the galaxy that we cannot see but that contributes to the mass. So explain how astronomers account for this discrepancy. Galaxy has more mass than visible. So possibly contributed by dark matter. There's 2 marks for this, so I feel like that on its own maybe isn't enough. I think we probably do have to make reference to dark matter. So it contains some dark matter. And that's it.